Okay, you can share, no?
Okay, very good. Can you see it?
Yes, yes.
Okay, perfect.
We have 4 minutes time. It is with your decision if you want to wait or you want to begin.
I think perhaps I just begin.
Mm.
So, hello everyone. You are very welcome to ask questions during the talk. I'm not sure if that's possible. If not, well, maybe at the end. Um, so this talk will be about the no boundary wave function and the density matrix of the universe. And so the Hartle Hawking or no boundary wave function of the universe is a very beautiful and well motivated idea. And I think it's the best theoretically motivated proposal for computing probabilities in cosmology. Unfortunately, it seems to give the wrong answer. Um, and it seems to give a wrong prediction for our universe. And at some level, you can ask, well, how wrong? Well, you probably all know about the cosmological constant problem, which is that the vacuum energy in units in Planck units is 10 to the 120. Now, the problem with the Hartle Hawking proposal is exponentially worse. It's somehow the exponential of that number. In other words, that proposal, at least taken in the simplest context, would give an overwhelming probability for an empty universe with the present cosmological constant, or perhaps a lower one. And that would be by a factor of 10 to the 120, roughly. So that's you could call it the exponential of the cosmological constant problem. And you might say, well, this is another beautiful idea killed by an ugly fact. And we have known about this problem for a long time, so you can ask, why are we bringing it up again? Well, for black holes, we have learned that the gravitational path integral gives us the right answer once we properly interpret it. And this has been shown for the case of the black hole information problem recently. And so it seems appropriate to revisit this old problem to understand it better and more sharply. And one could say that it's a kind of information problem in cosmology, except that it's not a subtle issue, it's just a very big order one, or order e to the 10 to the 120 issue. Um, it's more dramatic because it represents an apparently very large conflict between the path integral and experiment. Now, the goals of this talk is, first, I will explain this problem in the context where it seems sharpest. So we'll discuss the no boundary proposal in the context of inflation, where I think this problem is a little more clear. Perhaps not as dramatic as what I just said, but a bit more clear. And then we'll discuss a slight generalization of this proposal to the density matrix of the universe. And unfortunately, we'll not solve the above problem, but I think it's a useful way to think about the no boundary proposal. So let's discuss this no boundary proposal. So this part is will mostly be a review. And so we'll present a version of this problem that seems to me most clear. And we'll concentrate on part of this problem, the part that seems better defined. So so this is a small sketch of the evolution of the universe. So the idea is that there will be an early inflationary period. That inflationary period ends at some time, which we call the reheating time. And then we have the usual hot Big Bang cosmology here in green. Um, and we'll approximate this reheating time to be instantaneous just for simplicity. And we'll view the later universe as being a classical measurement apparatus that is measuring the early universe. Now that's how we normally think about it when we think about the small fluctuations or the primordial fluctuations that we encounter in cosmology that we see through the cosmic microwave background. And this is a way to avoid anthropic issues or other problems that might arise if we try to directly think of us as quantum observers measuring the full wave function of the universe. So we're going to see ourselves as a classical measurement apparatus that is measuring the early universe, and in particular, we will be measuring the shape of this reheating surface, as we will be discussing in a second. So we imagine that we have an inflationary potential that is fairly flat in some region. This is just a sketch. I mean, any potential like m squared, phi squared might do for this purpose. But there is a region where we have slow roll inflation, and then we have here our vacuum, and we'll concentrate on this part of the evolution of the universe when the inflaton is in this region. And there is some value of the inflaton where reheating happens, and we'll always consider values of the inflaton that are higher than that value where the potential is higher. So we do this to avoid discussions of Boltzmann brains and other confusion issues. Eventually, we will need to understand such issues, but hopefully they will not be essential for the problem we'll discuss. And this is not completely clear, but it's perhaps reasonable. Now, this perspective works well for the primordial fluctuations, quantum fluctuations. Now, the Hartle Hawking proposal is the idea that the amplitude for configuration of fields and geometries and three geometries of the three-dimensional space are given by the action of a solution that ends at some future boundary on a three-dimensional geometry with some values of the fields on that three-dimensional geometry. Of course, this is a four-dimensional geometry and four-dimensional field. We evaluate the action, we put it in the exponent, and that gives us the probability amplitude. In principle, we can also compute quantum determinants, so the one-loop corrections, and further corrections as we can usually do in gravity viewed as an effective field theory. So it's a semi-classical proposal. So the first step is to discuss a classical geometry. Then we could consider quantum fluctuations around it. And in this talk, we'll just concentrate on this classical geometry aspect. So by these fields in three dimensions, what I mean is the geometry of a slice, of a three-dimensional slice, and the values of the fields. In this case, we'll just consider a single field, the inflaton field, on that three-dimensional slice. And when I add the index tau, what I mean is that we'll have now the four-dimensional geometry together with the fields that live in that geometry, and that will be a solution of the Einstein equations. Now, we will pick a complex solution that will have an excursion into positive imaginary times at early times, and that's the aspect that was present in the Hartle Hawking no boundary proposal. And this complex solution has no boundary at early times. Now, more generally, one could say that it's a complex metric obeying the Kontsevich-Siegel-Witten criterion that was discussed recently. If you know what that is, if you don't worry, I'll explain this. Now, the simplest case that would be the case of empty de Sitter space. So this is the metric of empty de Sitter space. It represents a contracting and expanding universe. And we can analytically continue time to I theta, and then we get the metric of a force sphere. So the Hartle Hawking idea is that we go back in time up to t equal to 0, and then we make an excursion into imaginary time where we get the half of that four-dimensional sphere. So in terms of the complex time coordinate, we just follow this complex contour in the time coordinate that we see here. Okay. Or we could think, yeah, so basically that's the idea. Now we could consider now de Sitter plus a scalar field. So we could imagine we have this de Sitter space, and now we have a scalar field, and we fix a profile of the scalar field in the future. And then what we do is, in this case, we consider a classical solution of the wave equation, which is smooth on this geometry, on this complex geometry. Now, in general, it will be a complex solutions because we are deciding to go into this complex direction. And then we evaluate the action on that solution, and that gives us the probability amplitude. Just as an example, if we chose flat slices, flat slicing of de Sitter, then we have the simple solutions. So this is the Fourier components case here, the modulus of the three-vector k. And then the prescription of going to imaginary time in this context would be to give some imaginary time, imaginary coordinate, imaginary component to this conformal time coordinate at early times. And because the solution is complex, when we evaluate it in the action we were seeing before, then we will get that psi square is not just 1 because the action is not real, and then we'll get a non-trivial probability distribution for the Fourier components of that profile that we fix in the future. So this is a way to get that wave function. This is a way to get a wave function in this approximation. It's a Gaussian wave function. And this is completely equivalent to what we would get if we use the so-called Bunch-Davis vacuum. Now, we could do the same thing using the coordinates we discussed before, and the solution is just slightly more complicated, but it's basically the same thing. And as I said, this is the same as the usual state we get in de Sitter space. But we described it in this way so that the connection to this Hartle Hawking proposal is more clear. Okay, so we get exactly the same answer if we apply the Hartle Hawking proposal. And furthermore, this proposal is well defined for an interacting quantum field theory in de Sitter space. And it's well defined once we include the period of Euclidean time evolution. So that dumps the very high frequency components and gives a well-defined state. And in fact, this is actually also how we pick the state for the Minkowski vacuum in an interacting field theory, similar to the I epsilon prescription. And actually, in some sense, this prescription, you could think of it as more fundamental because actually the vacuum in our Minkowski space is determined by cosmology. So it's even more fundamental. Now, this also works when we include dynamical gravity. In particular, this works also for the case of inflation, where we have a scalar field plus gravity. And for perturbative fluctuations, for small fluctuations, when the spatial slices are almost flat, it gives the standard inflationary results, which are in agreement with observations. Now, so for inflation, just a bit more words. So we have a three-dimensional geometry and a scalar field, and then we can fix the scalar field. So there is a certain gauge symmetry, so we can choose various slices, and so we can choose a gauge, which is essentially a choice of time, where this scalar field is a constant, and we take that constant value to be basically the value at the reheating surface. So that's a special surface during the evolution. We could pick some other time, so this is a good one to pick, so that which is a time at which something special happened. And then we can ask what is the shape of this surface, right? Now the shape involves various functions in the three-dimensional geometry, and it involves sort of tensor fluctuations and scalar fluctuations. We'll just focus on the simplest one, which is the so-called scalar fluctuation, which is basically a deviation from the flat space metric by an overall scale factor. Okay. We could also include the tensor fluctuations in this discussion, but the result is not very different. Okay. So the new aspect of the Hartle Hawking proposal is that it also gives us a method for computing the probability of large fluctuations. So we could, in principle, compute the probability that the reheating surface has a very large fluctuation of this form in its shape, and not even that, but even some big fluctuation where the reheating surface now changes the topology, if you wish, or forms a spherical shape or some closed shape of this form. Now, particular cases when we consider that reheating surface have the shape of a sphere, let's call it a spherical universe. And in that case, we can certainly calculate this. It's a simple matter of solving the equations. And I won't tell you what the solution, well, I won't present the explicit solution, but the answer involves a non-singular geometry, and it's complex. And it involves a finite sort of region of the usual inflationary trajectory. And so it starts in the future as you evolve to the past. It starts almost real in the future with small complex deformations. And then when you go to the past and you get to the point where the whole reheating surface or that whole universe becomes in the past of the order of horizon size during inflation, then we essentially go into imaginary time. And it's somewhat similar to the de Sitter case and can be viewed as a small deformation from that de Sitter metric. And so it's a geometry roughly of the same shape that we discussed before for de Sitter. The new feature is that when we evaluate the value of the action, we get the action receives most of its contribution from this region where the metric is mostly Euclidean. That the value of that action is just the usual value of the Sitter space, which is, this is the action for the Sitter for a constant V. But here we get the potential V evaluated at roughly the point at the value of phi where we have this excursion into imaginary time. So let me call this phi of 0, could be phi here at the tip or phi at at the place where the big universe becomes of the order of horizon size. And now this expression has an interesting feature, and so we could consider two possible spheres. So a small sphere, this is the purple sphere here, or the green sphere, which is a bigger sphere. And this proposal allows us to compute the relative probabilities of having a reheating surface with a spherical size, which is either the small one or the big one. When we pick the small one, we have to go back in time a certain amount. And when we pick the green one, which is bigger, we have to go back in time a bigger amount. And so when we go back in time, so this is the time of the reheating surface, we go back in time a smaller amount, we encounter this value of the scalar field here in the region where the metric becomes complex. And when we have a bigger sphere, we go back in time a bigger amount, so the value of the potential for the green sphere is a little bigger. And what that means, since the value of the sphere is a little bigger, the value of the potential here is a little bigger, is that the probability for the green one, which is this one, will be much smaller than the probability for the purple one, which is this first one. So the conclusion is that it is much more likely to have a small sphere in the future than a bigger sphere. So we can also express this as saying what the probability of having a certain number of e-folds of inflation. So here you can imagine, you can say that the universe started here, and then we had a certain amount of e-folds of inflation, or the universe could have started in this green sphere, we would have had a bigger number of e-folds. And so the probability of extra e-folds of inflation can be easily computed from the previous formula. So it's just the probability, it's just moving a little bit the field up or down according to the solutions of these equations. And one can expand this potential. And once one does that and one does the math, one finds that the probability of having some extra number of e-folds of inflation is 1 over the amplitude of scalar fluctuation. So it's the same combination of the potential and its derivatives that determines the amplitude of scalar fluctuation. So the fluctuations we actually measure in the sky. So if we use the experimental value of the amplitude of the scalar fluctuations, we get that the probability of extra e-folds of inflation goes like 10 to the 9 times the delta n. So it's a huge, very large suppression for extra e-folds of inflation. So you can say that this is a pressure that wants the overall, if the universe had some overall spherical shape, it would want that spherical shape to be as small as possible. And so that's the problem. So this is a problem because we don't observe this spherical shape for the universe. The universe at long distances appears to be flat. If we said, well, what if it is a little bit more curved? So it has maybe a sphere which is much bigger than the size of the observable universe, let's say a factor of, well, what's consistent with the experiment now, it's maybe about a factor of 100 bigger than the observable universe. But let's say you say, well, it's a factor of 10 bigger. Well, then that would be more likely by this factor of e to the 10 to the 9. So it's a huge probability pressure to have the universe have positive curvature and be very small and very small amount of inflation. Now you could say, well, anthropics limits this, but suddenly, well, it looks like it wouldn't be limited. I mean, you could have a universe which is just slightly more curved than it is measured to be. So that doesn't seem to run into any obvious anthropic issues. So this is the problem. So I think this is the sharpest way to understand the problem, which is, and I would like to make perhaps some comments. One is that the small primordial fluctuations that we usually discuss in inflation can be viewed as fluctuations in the scalar curvature of the reheating surface. And you can view the size of the S3 as a spatially constant mode of that scalar curvature. So we're not talking about a different observable. We're talking about the same observable for which we now use quantum mechanics to describe its probability distribution. And this is just a different, let's say, mode of that observable. So it's very closely related to the type of, it's a basically the same type of observable for which we use quantum mechanics and we have successful predictions. So we go slightly beyond what we usually discuss, and then we encounter a problem. So we have a theory that works beautifully for the spatially non-constant modes, but fails miserably for the spatial constant mode of the scalar curvature. And as far as I understand, anthropics that doesn't seem to help solve this problem. Now, I think this is an important problem in quantum gravity, and if well, maybe you've already heard about this, you understood it this way, but if you didn't, I think it would be useful to review it and understand it in detail. Now, there are many possible answers. So this is an old problem, so maybe not expressed it this way, but it's an old problem, and there were many different possible answers people have given during the years. And I will quickly review some of them. One is that, well, maybe this method doesn't work because the Euclidean action is not well defined, it's not bounded below, the theory is not renormalizable. Now, the issue of the non-positivity of the Euclidean action is related to the fact that the positive curvature contributes negatively to the Euclidean action, and that's why we got some probability that is bigger than 1, so it's actually not normalizable, not normalized. Now, the idea is that this fact that the action is unbounded below is solved by a suitable analytic continuation of the contour, so we don't integrate along all real metrics in the path integral, but for the scale factor, we choose an imaginary direction. Now, the idea of not being renormalizable, that maybe can be solved by going to string theory, perhaps, or some more UV complete theory. So there are many other cases where these Euclidean methods or even complex metrics are giving us the right answer. For example, for Euclidean black holes and for applications to the black hole information problem. Also, the recent progress involved complex metrics that involve non-trivial topologies, for example. So we are just simply applying the same methods that work very well in one context to the cosmological context. Now, a related context is that this no boundary proposal actually works beautifully in the ADS case, or the anti-de Sitter case. So there, if we're interested in Euclidean ADS EFT, so we have Euclidean ADS space, which is the same as hyperbolic space. So, and in that case, the quantum gravity on this Euclidean hyperbolic space is supposed to be the same as a conformal field theory that lives on the boundary, so Euclidean field theory. And in that case, we have the same type of action, which is 1 over the potential. Here, I just simply expressed it in terms of the radius or of the space, radius of curvature. And in this case, there are some explicit examples where one can compute the action, the Euclidean action on both sides, and on the gravity side and on the field theory side. And in this case, it agrees perfectly, including the overall sign here in the action and the coefficient and so on. And not only that, but even the quantum corrections also agree. So it's a case where it works very well. Now, there is also a very close relationship between ADS and DS gravity results, just at the level of gravity. We don't know what the precise DS CFT case is, but at the level of gravity, we have, they're very closely connected. Now, one could say that in this ADS problem, in the ADS situation, the problem was Euclidean to start with, so it's more reasonable that something like the Hartle Hawking proposal would work. Now, So recently, developments have highlighted the importance of taking the semi-classical path integral carefully. Now, another possible answer is that perhaps we have some different initial condition, perhaps set by some other dynamics, perhaps the dynamics of eternal inflation. And I would say this is probably the idea that most cosmologists have about the solution to this problem. Now, one comment about this is that there is one case where, even if you take that point of view, the Hartle Hawking proposal is giving the right answer, which is the case of slow roll eternal inflation, where there you can compute the probability distribution, and it's given by the Hartle Hawking answer when the potential is slowly varying and has a minimum value which is bigger than 0. So this suggests that the Hartle Hawking proposal works in a landscape with a positive minimum potential, and it's giving us the answers that are correct after reaching thermal equilibrium. So this is a context in which the Hartle Hawking proposal actually gives an answer that can be derived using different methods that will also tell us what a possible interpretation of that proposal. Now, maybe in some sense, we're in a young universe that hasn't reached equilibrium yet in the space of configurations. By the way, this is similar to the solution of some other paradoxes, like the Olbers paradox. Now, so that might be an answer, but then we would have, of course, the problem of understanding what set the initial conditions for the universe. Now, another possible answer that people have given, especially Vilenkin, is that we change somehow the sign of the action, so we interpret the same wave function as resulting from some tunneling effect, and it's somewhat related to the previous answer that we start in a different state. In this case, we start from a very tiny universe, and we interpret the action as giving us the probability that we tunnel to a bigger universe where the solution can become Lorentzian. And now, if you take this point of view, then the sign of the quadratic action for the small fluctuations would be wrong. So this would give the wrong answer for the small fluctuations. Now, we could fix this at the cost of making the origin A equal to 0 special. So that's the proposal that Vilenkin and collaborators have proposed. Now, there is another proposal that's been given by Hartle Hawking and Hertog. And the idea is that this proposal, that the Hartle Hawking proposal is correct, but there is some selection effect, so it's anthropic or related, that pushes us to have a large amount of inflation. So the idea is that the idea of this proposal is that it is that we as observers are very improbable. And so then when we compute the probabilities, there is the usual factor that we discussed before. And then there is the small probability of having an observer per unit volume. And then there is a factor that involves the present volume of the universe. And that factor of the volume involves a factor which is of order e to the 3n, which is the number of p-folds. And then, so this is a factor that increases with the number of e-folds. This is a factor that decreases with the number of e-folds. And so maybe there is a maximum saddle point contribution. And so this can work if the probability of having an observer is very, very tiny. An observer per unit volume is very tiny, at least as tiny as this. So this is a very tiny number if you think about it. But yeah, so something like this might be the answer, but it would be nice to understand better where this comes from. And now the conclusion so far is that the no boundary proposal is very interesting and influential, and it seems to lead to a paradox, which is more serious than the black hole information paradox, I would say. And so that concludes the discussion of the Hartle Hawking proposal and what I think what most people think is the main problem with this proposal. Now I would like now to describe some work we are doing on the density matrix of the universe. We can call this the no boundary density matrix. It's something we are doing with a student and a postdoc at Princeton, Victor Ivo and Yue Shou Li. The problem described so far is not what we really want to solve. So in the following sense, we should, in principle, consider only the observable part of the universe, and we would like to predict probabilities for the observable part of the universe. And for that reason, we are tracing out over the unobservable part of the universe. So this is the same diagram that we had before. And so the green part is the later evolution of the universe. And we are here now, and we are observing into the past. And we observe only a finite region of the reheating surface. So a finite region of the universe. And that's all we can observe. There might be something else outside, but we don't really observe it. And so what we really want to compute is a density matrix where we have basically the 3 geometries. So the 3 geometry of the Brand, the Ket entries of the density matrix. So the wave function depends on only 3 geometry, but the density matrix depends on 2 of them because one is the Bra index and the other is the Ket index. So here the index is just the full 3 geometry of the universe. So that's why here we've indicated 2 possible 3 geometries in green. Hopefully this is clear. So plus and minus are the Bra and Ket entries of the density matrix. So in other words, we have some 3 geometry that there is some observable region, which is the in the region in the in means that is in the region that we are observing, and then the out region is the region outside our horizon, so we don't observe the geometry in the sigma out region. So if we had a wave function for the whole universe, then what we would need to do is first make the density matrix out of psi and psi star, and then set the out geometry to be equal in psi and psi star, and then integrate over the out fields. So all the possible values of the out fields and the possible values for the out 3 geometry. Now, when we do that, then we expect, since we're making a classical approximation for this, for the wave function part, we expect that this integral will also have a saddle point approximation, and therefore there will be a saddle point value for the geometry outside. And so in the end, we are going to be evaluating this quantity for 3 geometries and values of the fields and the out region, which are obey these saddle point equations. Now, what are those saddle point equations? Well, now in this out region, we'll have some new boundary conditions. So we'll have to solve now a classical problem with new boundary conditions in the out region. So in the out region, we have that well, first of all, the geometry has 2 sheets for the plus and minus entries of the density matrix. And in the out region, the plus and minus are going to be equal, and the conjugate momenta in the plus and minus are also going to be equal. So the first equality has to do with the fact that we are setting here the plus and minus regions in the plus and minus fields in the out region to be equal. And the second equality comes from the saddle point approximation. This says that if you make small variations here of the values of these fields, the action should not change. And now small variations of the values of the fields amount to, if you just want to calculate the change in the action, that's the same as the conjugate momenta, and that's why they should be equal. So these are the boundary conditions in the unobserved region. So we basically, the idea is that if we want to compute the density matrix, we just now compute a solution of the classical equations on a 2-sheeted geometry, where in the observable region, we have some boundary conditions given by the values of the fields we are interested in. And in the out region, we have some boundary conditions that are set by this. And then we compute the 4-dimensional action, the 4-dimensional solution, and we compute the action, and that gives us the density matrix. So here is another picture. So we have a picture where we have the 2 sheets for the Brand, the Ket, or 2 sides of a Schwinger-Keldysh contour. This type of contour is familiar from real-time computations in, for example, thermal field theories. And And these boundary conditions along the out region can be viewed as part of the no boundary region. So they are, since we are gluing the momenta and the positions, it makes the fields essentially continuous across this boundary. And so it's essentially similar to a no boundary region. So the only boundary really is this little slit. In fact, the fields are equal here, so we can move this out region. We can move it all the way back to the backwards light cone of this region, and we get the same answer. And so that's another way of representing the geometry. So the only part of the geometry that is relevant for our calculation is the part that is in the backward light cone of the observable region. So it's manifestly clear in this way of doing the computation that we don't care about the region of the universe that we do not observe. So it's not that we have to first compute the wave function in that region and then trace out, but we just have to compute the classical solution only in the past of the observable region, which is what one would expect to need. Now, the question is whether this changes the geometries we should consider, and the answer is that it does change them, but it changes them in a little bit. So it only changes them in a small way. And so it does not change them enough so as to solve the main problem. But it's still worthwhile understanding in more detail what these geometries look like. The main reason that we get the new geometries when we evaluate this density matrix, this classical density matrix, is that we're evaluating the probability away from where it wants to be somehow. So the universe wants to be small, and we're trying to evaluate it in a universe that is large. And so for that reason, the probability is sensitive to the precise question that we're asking. So for example, we could choose this region inside the horizon to be a ball with some fixed area and some fixed curvature inside, let's say positive or negative. And we will not discuss the details of the solution now. They are SO3 symmetric, not SO4 symmetric, but let's give a quick flavor of the solution. So the idea is that we have some observable region of the universe, which has the shape of a ball. So it's a two-sphere boundary with a three-dimensional interior with, just for the sake of the argument, let's say we have a constant curvature geometry here in the interior. We fix that geometry, and we could fill the outside in different ways. We could fill it with a sphere, we could fill the outside with an infinitely extended universe, and so on, and we should pick the dominant one. And the dominant one appears to be the one with spherical topology. So we have that region that we cared about, and then we have, we fill the universe with spherical topology. We could fill it with a bigger sphere outside or a smaller sphere, and so on. Now, here in this region, we'll have some boundary conditions that tell us that the curvature should be constant. In the outside, the curvature could be constant or not constant, but it has to be the same on the plus and minus sheets of the solution. Now, for example, if we imagine we had a universe here, a piece of the universe which is like a piece of a sphere, a piece of a big sphere. Let's say it's a piece of this big sphere. And so one option is to just fix the whole universe to have that constant curvature everywhere. And the other option is to say, well, that curvature is constant in this observable region, but outside it can be whatever it wants to be. If you relax the condition that the curvature is constant outside, then it will become non-constant outside. And the reheating surface will become a bit smaller and with varying curvature, but still will have the topology of a sphere. And so you'll get a new solution. And perhaps not surprisingly, since the universe wanted to be smaller, once you relax the condition that the curvature should be constant outside, we'll get a slightly smaller universe. But of course, we are putting here the condition that this sphere has to have a given size. Okay, so it can become very small. Okay, so this is one case where we get the locally reasonable answer. So the potential now so in this case, So in this case, we still have this pressure for having a smaller universe. Now we'll discuss another case where we get at least a reasonable answer locally. By locally, you'll see what I mean. So we'll consider now different potentials. We'll consider potentials which allow for bubble nucleation geometries. So imagine that we now have a potential which has this shape. There's a potential that similar to the one that we had before, but now we have a little dip here and a barrier. So if you start the universe at this position, it would inflate forever in de Sitter space, at least classically. However, there is a small probability that will tunnel here, and there is a solution that describes that tunneling from here to here, which is a solution that has a topology of an S4, but is somewhat deformed, and the scalar field interpolates between some value at the north pole of that force sphere and a different value at the south pole of that force sphere. And so it's a universe that has S3 slices, so it has SO4 symmetry, not SO5 symmetry, and so on. So this is a solution that was discussed originally by Coleman and DeLuce. So we'll now think about those solutions. So but when you think about these solutions, then you can continue them to Lorentzian signature. And in Lorentzian signature, the analytic continuation can be done in such a way that, let's say there is a three-dimensional geometry here that goes between the North Pole and the South Pole. That three-dimensional geometry becomes something with a topology of a three-sphere at this moment. And then you evolve that in Lorentzian time, and what you find is that these original S3 slices that had the geometry of an S3 become the geometry of three-dimensional de Sitter space. So what was here an SO4 symmetry becomes an SO13 symmetry, the symmetry of three-dimensional de Sitter space. Okay. Now, in this Euclidean geometry, these S3 slices were becoming zero at the north and south pole. Here, these DS3 slices are becoming zero at this point, and at that point, actually, they become zero all along these blue lines. But those are not singularities of the geometry. They are simply, the geometry can be continued beyond that point, and these three-dimensional slices become slices of hyperbolic space now. So now hyperbolic space also has the same symmetry as O13. And in this region, these H3 slices are slices of constant time. So now the direction perpendicular to the slices in this region is a time-like direction. And so you can view this as expanding bubble. So this is like an expanding bubble of the new, you can view this as an expanding bubble of the new vacuum. And this is the old vacuum. That's one possibility. This becomes most clear if you think of this problem in the thin wall approximation, where the whole solution, the region where the scalar field changes is constrained to be, well, it happens to be on a thin region. Let's say it could be one of these slices. In that case, we would have the domain wall here along this orange slice, and on this side, we would have one of the vacua, one of the values of the cosmological constant, and we have another one here. Now, in this case, recall that the potential we were discussing is a potential like this, so that after this, if we start the scalar field here, we'll have an inflationary region here when the scalar field slides down the potential, and therefore here in this region we'll have an inflation. So we start with this H3 slices having high curvature at the horizon, and then there is a period of inflation where that curvature dilutes, and we would get a very tiny curvature in the future. And these geometries certainly were discussed in the context of eternal inflation, and is one of the ways in which people think that our universe could have been created. Now, the idea is that these geometries can also be reinterpreted from this density matrix point of view. So the idea is the following. Suppose that we are interested in a 3 geometry that has the, let's say, geometry of a ball, but with negative curvature and some value of the scalar field. Then there is a special value of that negative curvature, which is the value that occurs on this solution, so where the scalar field, let's say, reaches the reheating size at some reheating value at some point, then there is some value of the curvature in that region. And if the universe, if you're asking about the density matrix of the universe evaluated on that particular 3 geometry, then this solution we've been discussing would be a possible classical solution. And the solution contains 2 sheets of the solution we have discussed. And so I try to represent here the 2 sheets. So 2 Lorentzian pieces here. It's only a piece of the Lorentzian part that we get. So the piece that is in the backwards light cone. And then we could put the final boundary condition well along any spatial slice, but it's convenient conceptually to move that slice backwards along the backward light cone, as we explained, and then along this spatial slice of the 3-dimensional geometry of this Euclidean section. So then the idea is that we have these 2 sheets, and then on one side of the sheets we go in Euclidean time in one direction, and the other side, the side of the cat, let's say, we go in the other direction. And so the geometry, so here in this plot, I've drawn the Lorentzian geometry along the vertical direction, and the Euclidean geometry is coming out of the page and into the page, and it's spanning this region of the Euclidean geometry. Hopefully this is clear. So this is, on the left-hand side, is the same as this blue region in the right-hand side that is now viewed from the top. And here you should imagine these 2 as this one coming out of the screen and the one here going behind the screen. So in this way, so we have the Lorentzian geometry up to here, and then Euclidean geometry that connects the bra and the cat, similar to what we have in a thermal, we would have in a thermal field theory. So that's another picture of the same geometry where we removed the part that we are not observing. So these are the 2 sheets of the Lorentzian geometry. And this is another way of drawing the same geometry where we have the Lorentzian, the 2 Lorentzian sheets, and then we have a Euclidean direction that is essentially forming a circle. So if you go back here and you think about this, let's say this line here is forming essentially a circle, a Euclidean circle that is joining the bra and the cat regions of the density matrix. So we have a contour roughly of this form, and I've drawn it this way because it's very similar in spirit to the Schwinger-Kaldish contour that are encountered in thermal systems. So in a thermal system, we would have evolution on Euclidean time, which is a circle, and then we evolve in Lorentzian time along the, let's say, bra and cat sheets of the contour. Now, in ADS cases, people have discussed this, and then you get a geometry which looks like this, and you have a black hole, typically a black hole horizon, and then this line is along the black hole horizon. In fact, I have here a picture. So this is taken. So this is the kind of picture that was written, for example, in what was plotted in this paper. So I took this picture from this paper here, which was discussing the ADS case. In that case, this circle is at the ADS boundary, and this part here is the Euclidean black hole, and here we have a Lorentzian black hole. This is rather similar, but the difference here is that this circle was, in their case, the circle was at the boundary, which has been imposed by the boundary conditions by hand somehow, by saying what problem we are solving. In this case, the circle is at r equal to 0 in the geometry. It's not really a boundary. It's, let's say, where the observer in the future will see that are equal to 0. And this is a smooth region of the geometry, not the asymptotic boundary of the space. But this right-hand side part of the geometry is somewhat similar in the sense that this region is a bit somewhat similar to the cosmological horizon. It's just the horizon for it's just the backward light cone of this observable region. Okay. Now, I think this density matrix point of view might be useful for questions about the measure problem in eternal inflation for the following reason. So we have usually in eternal inflation, we have, let's say, some unstable vacuum, which is the blue one, that can decay into various other vacua. Some of them continue inflating, like the green region or the purple region here, and some of them might inflate for a while and then perhaps end up in flat space. Those would be, let's say, the red ones. And so let's say we encounter ourselves in one of this vacua with, let's say, in the red region, and so we'll have some end of inflation inside here. We're in one of them, and then you might worry that well, there are several copies of us. So what about the probability that maybe we are some observer around here and so on? And the idea is that from this density matrix point of view, we only have to worry about this past light cone of this observer, of the observer we had in the previous transparency. And then we go into Euclidean time, and that Euclidean time solution is essentially the same as the solution that we use to calculate the decay from the yellow vacuum to the red vacuum. And we don't need to talk about the rest of the universe anymore. So we just concentrate on this. So we just concentrate on this region of the universe, and that's basically all we need for the description of our universe. Now, in principle, we should sum over all bubbles that lead to our observable universe. So it's not just the one bubble that goes from the yellow vacuum to the red vacuum, but if there was a possibility of going from a green vacuum to the red vacuum, which is the one we're in, then we should sum over that one too. So in principle, we have a sum over all those bubbles. And this is somewhat similar to what we get from the eternal inflation point of view, because there we would say that the probability of the decaying from a parent vacuum to our vacuum is related to the, let's say, the Hartle Hawking measure factor for the parent vacuum times, well, let me say it differently. The idea is that this decay rate is equal to the action of the bubble divided by, let's say, the action of the parent vacuum. And then if we want to compute the probabilities, we have to compute the probability that we were in the parent vacuum, which would be given by this Hartle Hawking factor, and then this decay probability. And so in the end, we are summing over all these bubbles. But the idea is that from this density matrix point of view, we just have to consider this sum with the same sum, but with slightly different logic, that we are interested in the density matrix of the universe, and then we sum over all Euclidean geometries that can end on that geometry. And now you might say, well, here you get the same answer, so why do I care about this new point of view? It is the same as what was said before. However, it's interesting that not all relevant bubbles come from the sitter parent. So there are situations where you can have those bubble geometries where there is an end of the world brane on one of the sides, or even there is an ADS vacuum on the other side. So the Lorentzian pictures are like this. So here we have the inflationary region, and we have an end of the world brane. There is nothing on the other side, or even there is on the other side we have an ADS vacuum. So here we are not interpreting this as the ADS vacuum sort of up tunnel into the inflationary point of view, or maybe you could interpret it that way, but that's not normally discussed. But from this point of view, we don't have to give it such an interpretation. We just can view this as a contribution to the wave function of the universe, or the density matrix of the universe, sorry. Oh, I didn't discuss, there is one point I forgot to discuss, which is that, so all the solutions that we've been discussing so far are discussing are correspond to this real solution that is real in this Lorentzian region, and that will occur for a very special value of the spatial curvature here, which is the value that occurs on this real solution. If you're interested in evaluating the wave function, the density matrix of the universe for a different value of the scalar curvature, the solution will become slightly complex. And then you can ask whether those other values will have higher or lower probability. And it turns out that they have lower probability, and the computation of geometries that are just a little away from the geometry that we discussed, or small perturbations away from the geometry we discussed, the real geometry. That computation boils down to the same as the computation of scalar fluctuations for open inflation. So this type of geometries were considered previously in the context of open inflation, and it was found that the spectrum of perturbations is an ordinary Gaussian with the right sign. So that means that this is a local maximum of the probability. Very good. So the conclusions from this density matrix part of the talk is that we can directly find the geometry for the density matrix of the observable region, and it has similar features and problems for the like this problem of a small amount of inflation we discussed in the very beginning, but it's a slightly different geometry. Now, then we discussed the fact that if the potential has some features, for example, this little bump, then there can be a real solution, and which would be a local maximum of the probability. The solutions we find in general for generic potentials without any special features, then those are always complex. And the fact that they are complex is related to the fact that the universe would want to become smaller, or at least we are evaluating it at a place where it's not a local maximum of the probability. So if the potential has some features, then there can be a real solution, and it's a local maximum of the probability, though it might not be a global maximum. And the geometries are closely related. They're essentially the same as the usual. They are the same as the usual bubble solutions for a special value of the curvature, but we could also evaluate it for not those special values, but slightly different values. And in that case, we get the wave function around those or the density matrix around those points. Okay, thank you.
Thank you. Very, very nice talk. So I think there are some questions. Let me hello all. Anyone ask question can unmute the microphone and ask question. Also, we have some question in chat box, I think.
I think Shaheen has his hand up.
Yes, Professor Sheikh Jabari.
Hi, Juan. Thank
Hi,
you for very insightful talk. Actually, I have a very naive question. How do we generate entropy of the universe in your setting? You assume that at the radiating surface.
So that's a good question. I don't have a good answer. So normally when we discuss density matrices, so in recent times, people have discussed density matrices and their associated entropies. So here, if we calculate, if we take a region and we fix its area, right, and calculate the entropy. So there are different problems you could consider. So one is to consider a region of some size, any size, and calculate the density matrix, and then calculate the entropy of that density matrix. Then the most probable size for that region will be to be at the waist of the de Sitter space, and you'll get the de Sitter entropy from that way of thinking about it, where you don't fix the area of the surface. Okay. Now, if you fix the area in the far future, I suspect you might get perhaps some term involving that area. So, well, the short answer is I don't know exactly what entropies you get because it depends on what you keep fixed. So this is so in the case that you don't keep anything fixed, then you'll essentially get the de Sitter entropy in the at least the Sitter case. Now the question is what's more physical to keep fixed and so on, I think. So the short answer is that I don't have much more to say than well, what I just said about the de Sitter case.
Can I ask another question?
Yeah.
So are you naively thinking whether we still have something like a generalized cosmological principle in your setup, in the sense that you had this sigma plus in and plus minus in, and I would naively think that if you move this on your surface of reheating, the end result should not change. It should not depend on the sigma. Correct.
Should not depend on what? I didn't understand.
It should not depend on the sigma, the surface that we have. You have considered.
Yeah, that's right. Okay, so let me clarify that point a little more. So maybe, yeah. So we are evaluating the wave function on different three-dimensional surfaces, right? Let me go back to this diagram.
Okay. Right.
Now, we are evaluating it at as a function of let me say some three-dimensional surface and some value of the scalar field, right? Now we can change this three-dimensional surface and also the scalar field so that they're on the same classical trajectory, let's say, for example.
I see.
If we do that, then the probability doesn't change.
Okay.
However, if we fix this value of the scalar field and we pick two different values for the sigma 3 for the same value of the scalar field, then the probability does change.
Okay.
Right? So that's related to the gauge, well, to this issue of the gauge symmetry or time reparametrization symmetry. So let me say it in a different way. So there are sort of gauge orbits along this space. So this space has some identifications that have to do with the time translations.
Yeah. Okay. So this is just like standard gauge symmetry of
this is the standard thing, and in order not to talk about that, we've chosen a special value of the scalar field, the value that corresponds to the reheating time, the reheating surface. And so then once that amounts to a choice of time, essentially. So there is some time at which something special happens in the universe. And then we can ask about the shape of that surface. And the shape of that surface, then, well, then all different shapes are all different configurations, not related by any gauge symmetry. And the probabilities are in principle different for all of them.
And one last question. In your analysis, you considered basically geometries which respect SO4 or SO3 in some cases, symmetry. And then I was wondering whether there are perturbations which can grow if you basically break this symmetry. So
no, there isn't. Well, in some cases we considered also the case with less symmetries. I think it's conceptually the same. Maybe some aspects are a little technically more difficult, but not, I think, conceptually more difficult. In the case of, for example, in the case of the bubble nucleation geometries, let me see where the bubbles. Yeah, so in that case, there is if you don't restrict to the spherical symmetry, then you have to worry about some modes that have to do with essentially the motion of the bubble or fluctuations of the bubble wall, which are a bit more like tensor modes. So, so they're included within the tensor fluctuations.
I was actually sort of concerned with this mixed master type geometries that discussed by Meissner some years ago.
Okay.
So in principle, there could be some configurations which are very far away from spherical symmetry. And
Oh, yes, yes, yes. We did not consider those, but yeah, one could consider them. And this no boundary geometry in principle also works for configurations that are very far away. In some cases, they are very, well, there are geometries that are very complex in some sense. So they're quite different from the ones we were discussing.
Can we argue that their contribution is always suppressed compared to the spherical ones?
Well, I don't know of a general argument for scalar fields and so on. But if you consider, let's say, solutions, Euclidean manifolds with any topology, but that obey Einstein's equations with a cosmological constant, then the zeta is the one with the smallest action.
Okay.
There was an argument by Bishop along for this particular.
Thank you very much. Thanks.
Okay, Fabiano, you can also ask your question.
Yeah, can you listen?
Yes, I can.
Thanks for your nice talk. I am a big fan of your work, of course. I am working on the ADS DCFT correspondence. And you talked about the good connection with the DSC CFT correspondence, right, in the geometries. What happened if we include a new extension for this case, for example, a boundary, a new boundary with a tensor? What happened for the probability and the expectation values anyway?
Well, in DS CFT, so the zeta CFT, there is a boundary in the, let's say, future, right? I presume you are not talking about that boundary, but a new boundary, let's say, in space. Is that correct?
Yeah. Okay.
Yes, yes. So, well, one case where you would have a boundary in space is this case that we discuss here, for example, with an end-of-the-world brane or these ADS solutions. So in this case, in the far future, let's consider this ADS case. So in the far future, you have a space which is similar to the zeta in this region, right? But has a boundary here. And you can view that as, let's say, an end-of-the-world boundary. Well, maybe this is a little simpler. So an end-of-the-world boundary. This is similar to having in the ADS situation, we would have a conformal field theory with a boundary, right? So here we would also have a conformal field theory with some boundary, some sort of boundary here. And this case can also be interpreted in a similar way. Yeah, so people have discussed this in the past.
Okay. Thanks a lot.
Yeah.
And I think the next question, Aida Rasulian.
Hello. Thank you for the very interesting talk. So my question is about the first part of your talk and about the problem with the number of e-folds. Would it help if one assumes that initial condition is Euclidean ideas instead? That later goes with the Lucita phase. I mean, in the...
Well, one is restricted by the requirement that we are solving Einstein's equations. So if you have some solution of Einstein's equations where in the early universe you have Euclidean ADS, that's in principle allowed. I don't know whether it does help or not, but I would emphasize, so people have discussed, so let me connect it to something that people discussed recently. For example, Van Ransdonk and collaborators discuss geometries where you have Euclidean ADS, but with a boundary in the past, right? With another Euclidean boundary, and then the universe has some moment of Euclidean time reflection symmetry, and then you continue that to Lorentzian signature. So that's another that's another type of continuation you could consider, but that one is not within this Hartle Hawking no boundary proposal because it has an additional boundary. It has another boundary in the Euclidean space.
Yes,
I don't know if that's what you're asking, but at least I'm
yes, so
commenting.
if the, sure, okay. So if the Euclidean ADS is has an evolving ADS radius, okay. So I'm actually thinking about a specific model. I guess it's not a good time to discuss it anyway. Thank you.
Which model are you thinking about?
Oh, actually, I just have a model that this happens in it, and I was curious to see if this would help with your setup. That actually
well,
has
I
a
think it would be interesting to
ADS
consider
pattern.
other geometries. I think other possibilities.
Yes, yes.
I've discussed here the simplest. I presume that that would happen in more complicated potentials. So I was considering the simplest potential here. In the beginning of the talk, I considered the simplest potential, and then in the end, the other one with a bump. But maybe more complicated potentials could lead to other geometries in the Euclidean region. So that
Thank you. Thank you. Thanks a lot.
Right.
Okay, we have about 5 minutes to the next talk. So if still there are any questions, please ask. If no, we again thanks Professor Maldacena, and I hope we able to hold this conference fully in person and see you in future face to face.
Okay, yeah. So thank you for listening and best wishes for the rest of the conference. Yeah.